Hello friends. So now we are going to start a new chapter called as grammars. Now grammars is going to be very simple, very interesting. At the same time I say a bit difficult too. Why difficult? It will be difficult if you are not observed all my previous sessions, because in automata theory, in the TCS subject, everything is going to be following what we have already studied. So if you have skipped anything previously, so the chances of understanding this are going to be lesser. So let's get started with the grammars. So now coming to the grammars, over here, let's define the grammar. Now definition of the grammar is not actually make you clear the whole idea of the grammar, but within the next two videos, we should understand what is a grammar, because we will be instantly solving some problems on it. And that is something, as usual in TCS, is going to make the things more and more clearer. So coming to the definition of the grammar, we see over here, a grammar is defined, or a grammar is used for specifying the syntax of the language. And that syntax is represented using the notation G is equal to my V, T, P and S, where V is equal to my finite set of variables. Now variables over here are basically my capital alphabets as in the English. So I say grammar is G is equal to VTPS, where V is nothing but the finite set of variables. My T similarly is going to be finite set of terminals. Now what I mean by terminals, exactly opposite to variables. If variables are capital alphabets, terminals are going to be small case alphabets. The next is I have P. P is called as the finite set of production rules. So P is the finite set of production rules, and lastly S is called as the start variable. So that's how we define the grammar. G is equal to VTPS, where V is nothing but capital alphabets, my T is nothing but small alphabets, P are going to be some production rules which is going to be used for deriving the grammar. Of course, that is going to be the heart of the grammar. That is the one which is actually going to help us derive anything. And S will be called as the start variable. Moving to the next definition. So here we have context-free grammar. So I define a context-free grammar as a grammar is said to be CFG if all the productions are of the form A derives alpha. Now what I mean by that? I mean to say that when I say A derives alpha, A is going to be called as a capital alphabet, remember, which we called as a variable. So G is equal to VTPS, and over here A is nothing but that V. So A is a variable and alpha is anything which is in sentential form. Therefore I say grammar is said to be CFG if all the productions are of the form A gives alpha, where my A is a variable and alpha is in some sentential form. Now what I mean by sentential form, it should be able to derive some sentence. Let us take an example. So the example over here says I have my production rules something like this. Let us say my P is called as the production rule, and the production rule is S gives ASB, or S gives AA, or S gives simply a small a. Similarly, next I have A gives a capital A small b, or A gives B. Now if I look at this problem, let's try to understand what do you exactly mean by this. So I say over here that my S is capable of deriving ASB, right? Now, how is that possible? Using this production rule, S arrow ASB. Further, if I look at the next capital alphabet, remember a golden rule. The moment I get small alphabets, it is the end of it, because everything in small alphabet will be called as a string. Whereas if the string contains any capital alphabet, that is variables, I can further derive it. So if I see over here in S arrow ASB, that S can further derive me something. Now that something can be anything among ASB or small a capital A or small a. So let's say this time I say that my center S has given me small a capital A, and rest everything before and after it remains the same. So now the string which I have, or rather I would say a incomplete string, a, capital A, small b. Now my capital A can further derive something, and for A also I have a total of 2 combinations. So let us say among these 2 combinations, my A is selecting this combination B1. So I say A gives simply a small b, and small b remains over here. So can I say overall that my grammar, which is having this production rules, has finally derived me a string double A double B? Yes. So over here I say my grammar is defined as G is equal to VTPS, where V is nothing but the variables in whatever example we have shown over here. So my variables over here, I can see the capital alphabets, that is S, capital A. Next, I want to see the terminals. The terminal seems to be small a and small b. So I say small a and small b are the terminals. What are the production rules? What are the production rules? The one which we have put here in the brace brackets, that is P. So I say my production rule will be P, and the start variable or start state will be S. So that is how we define a grammar. G is equal to SA, AB, P and S, where P is stated below, and this grammar is capable of deriving a lot of strings, of which one string is AABB, right? Therefore, I define a context-free grammar as it is said to be a grammar if all the productions are of the form A gives alpha, where alpha is in some sentential form. That is, ultimately, after using all of the production rules, I should be able to derive at least one sentence. Then only I say the grammar is context-free grammar. So if the grammar can derive at least one sentence, we say it is a context-free grammar, else it is not a context-free grammar. So in the next session, we are going to do a lot of examples on this, as well as cleaning of the grammars to make the grammar context-free. See you in the next session. Thank you.